The quantum equations that govern how atoms and molecules behave have been known about for over 100 years, but solving those equations is another matter. In this episode of Qiskit in the Classroom, we'll show you how a hybrid quantum classical algorithm called VQE can help. For pretty much any question you might have about the chemical properties of a molecule, the starting point is finding its ground state, the lowest energy configuration the molecule can settle into. The problem is that computing ground state energies exactly is incredibly hard. The quantum mechanical equations governing electrons in an atom or molecule have been known about since the 1920s, but solving them exactly requires tracking the correlated behavior of every electron simultaneously, and the computational cost of that grows exponentially with the number of electrons. For anything beyond the simplest atoms, exact solutions are out of reach, and classical computers are forced to rely on approximations. For many problems, those approximations work great. But for many systems that chemists care about, like transition metals and other strongly correlated systems, they fall short. This is where quantum computers come in. A quantum computer doesn't just simulate quantum mechanics, it is quantum mechanical, which means it can naturally represent the kinds of correlated, entangled electronic states that classical methods struggle with. The catch is that today's quantum computers are noisy and error-prone, which means there are many promising algorithms that we won't be able to run at scale for several years. VQE, the Variational Quantum Eigensolver, was designed specifically for today's noisy quantum computers. It's a hybrid algorithm that combines quantum and classical computing in a way that tolerates noise and still produces useful results. VQE leverages quantum computers to do what classical computers find hard, and exactly what quantum computers are best at: representing quantum states. Then the optimization is performed on the classical hardware. Today, we're going to use VQE to find the ground state energy of the hydrogen molecule, the simplest possible molecule, and a natural first test case. I'll walk you through the theory that underpins VQE, show you how quantum chemistry knowledge guides the setup of the problem, and then we'll run the full algorithm on a real quantum computer and see how our result compares to the exact solution. Before diving into VQE, we need to cover some basics of quantum theory. If we want to find the ground state energy of a system, we can start with the so-called time-independent Schrödinger equation. H times psi equals E times psi, where H is called the Hamiltonian and is a function that captures the interactions of the system that contribute to its energy. Psi is the wave function, a mathematical object that encodes everything about the quantum state of the system. And E is the energy associated with the state psi, given the Hamiltonian. In linear algebra, this is what's known as an eigenvalue equation. Solving this equation means finding the energy eigenstates psi, also called stationary states. These are states whose measurable properties do not change over time. Once a system is in an energy eigenstate, it stays there. The eigenstate with the lowest energy is called the ground state, psi 0, with energy E0. This is the state a system naturally settles into, and it encodes the stable physical and chemical properties of the molecule. To get the exact ground state energy, we'd need the exact wave function, psi 0. For anything beyond the simplest systems, a few electrons at most, this is computationally intractable. The wave function lives in a space that grows exponentially with the number of particles, making exact solutions impossible for many systems of interest. Luckily, something called the variational principle gives us a way forward. It guarantees that for any trial wave function psi tilde, the corresponding energy expectation value satisfies E0, which is the true ground state, is less than or equal to the expectation value of H with respect to psi tilde. In other words, any guess gives an energy that's an upper bound on the true ground state energy. And this makes logical sense, since the ground state is, by definition, the lowest energy configuration. If there were some other state that had a lower energy than the ground state, then that would be the ground state instead. So, if we have a systematic way to try many wave functions and minimize the energy, we know that the lower the energy, the closer to the true answer, and VQE is that systematic method. To take a molecular problem like this and solve it with VQE, we first need to go through a number of steps to translate and simplify the problem for a quantum computer. First, we obviously don't know the exact wave function. We need to decide on a way of representing the approximate trial wave functions we will be using in a reasonable, physically motivated way. For the molecule, we can use something called a linear combination of atomic orbitals, or LCAO approach. The idea is that the molecular wave function will look something like a combination of the atomic orbitals of the two hydrogen atoms that make up the molecule. In the specific approach we'll use in this video, we further simplify even these already simple atomic orbitals to be approximated by a linear combination of Gaussian functions. We call this a basis set choice. Within our basis set choice, we can also consider things like the symmetry of the problem and ignore electrons that don't meaningfully contribute to the ground state energy to reduce the so-called active space of the problem. We won't go into these details here, but you can learn more about them by checking out the VQE module or the Variational Algorithm Design course, both on the IBM Quantum Platform. The last step in converting our chemistry problem into one that can be solved on a quantum computer is to actually map those electron orbitals to qubit states, and the Hamiltonian to observables on those qubits. This, again, could be a whole lesson unto itself, so I'll just point you to Lesson 4 of Quantum Computing in Practice, which focuses on mapping. The mapping step allows us to express the Hamiltonian in terms of Pauli operators, which are the qubit observables. Now VQE can begin. First, we need a way to systematically search over trial wave functions, which is where the variational principle pays off. In VQE, this search is done with a parameterized quantum circuit, also called an ansatz. The circuit prepares a quantum state psi that depends on a set of tunable parameters theta. Think of them as adjustable dials. By varying these parameters, we trace out a family of trial wave functions, and the variational principle guarantees that minimizing the measured energy over this family moves us closer and closer to the ground state. The quality of the ansatz matters enormously here. If the true ground state can't be well approximated by any state the circuit can produce, no amount of optimization will get you there. It would be like trying to get the perfect blue shade by mixing different reds. It's simply not going to work. So, we need to make sure our ansatz is informed by the same physical intuitions that guided our choice of basis set. Then the quantum computer measures the energy for a given set of parameters. And then that value is handed off to a classical optimizer, which determines how to update theta to lower the energy further. Putting it all together, the full VQE loop looks like this. First, we prepare a trial state with the ansatz, measure its energy on the quantum computer, pass that energy to the classical optimizer, update the parameters, and repeat. Now we're ready to run VQE on a quantum computer. We're going to do two experiments. First, we'll warm up by finding the ground state energy of the hydrogen atom. This is nice because it's probably the simplest imaginable atomic system, so it'll be easy for us to compare our results to exact theoretical calculations. The ground state energy of hydrogen is well known. It's minus 0.5 Hartree. It's a nice even number because the unit of atomic energy, the Hartree, is based on the hydrogen atom energy levels. We won't go into the details here, but the complex mapping procedure that we've described gives us a Hamiltonian for our hydrogen atom that looks like this. With just a single qubit and a 2x2 Hamiltonian matrix, we could find the ground state simply by diagonalizing the matrix and reading off the lowest eigenvalue. But that's exactly the kind of brute force classical approach that doesn't scale well. Diagonalizing an n by n matrix takes an amount of time that scales like n cubed. So for systems with many electrons and large state spaces, this quickly becomes intractable. VQE sidesteps this by instead preparing a parameterized trial state and measuring the energy as an observable. This trial state is the ansatz. We'll look at 3 different ansatze to see how well each does at exploring the full state space of the qubit. You want an ansatz with enough parameters that you're fully exploring the space, but no more than that, because each additional parameter adds more computational complexity to the optimizer. To see whether each ansatz is adequate in exploring the full state space of a single qubit, we'll take 5,000 random values for each parameter, then plot each trial state on a Bloch sphere. We want the surface of the Bloch sphere to be covered by the trial states. As you can see, the first ansatz with only one parameter only covers a ring around the Bloch sphere, not the entire surface. The next one, with two parameters, does a pretty good job of covering the full sphere, but the dots are more concentrated at the poles, so it doesn't cover the space uniformly. The third one, with three parameters, does a better job. It has a more even distribution of dots on the Bloch sphere. So, for this demo, we'll use the third ansatz. Our ansatz circuit then looks like this. Starting in the qubit state 0, we then apply 3 rotations around each axis, with a parameterized angle for each rotation. Then, after transpiling our circuit to optimize it to the specific quantum computer we're going to use, we can run it. For the execution step of VQE, we need to involve our classical optimizer. First, we define a cost function, which the optimizer will try to minimize. For us, this is just the energy of the state. Then we call the classical optimizer Kobola to select parameters each run that minimize the cost function, shown here. We found a minimized energy of -0.468, which is really close to the reference ground state energy of -0.471, but, as guaranteed by the variational principle, still just above that value. Finally, in the post-processing step, we can visualize the convergence of the optimizer across iterations, watching it settle toward the minimum energy. That was just the warm-up. Now let's apply the same method to the hydrogen molecule. In chemistry, we often anchor calculations to known physical parameters to make sure we're modeling the real system accurately. For H2, we know the bond length, the distance between the two hydrogen nuclei, is 0.735 angstroms, so we use this as an input to calculate the molecular orbitals and the total energy of the system. With H2, that total energy has two contributions: the energy of the electronic orbitals and the repulsive potential energy between the two positively charged nuclei. Following a similar mapping procedure as before, we arrive at the Hamiltonian shown here. Diagonalizing and adding the nuclear repulsion energy, our target ground state energy is -1.146 Hartree. That's the target we're trying to hit. Since H2 also reduces to a 1-qubit problem after symmetry reduction, we can use the same 3-parameter ansatz as before. We optimize and execute as before, this time allowing 15 iterations instead of 10 to give the optimizer a little more room to converge. The result, a computed ground state energy of -1.130 Hartree, close to the reference value. As before, we can visualize the optimizer's convergence across all 15 iterations, watching it home in on the minimum. And there it is. We just used VQE to find the ground state energies of the hydrogen atom and molecule on a real quantum processor. We started with the Schrödinger equation and a minimal basis set, and showed how a quantum computer can be used to converge on energies that match theoretical values to chemical precision. VQE was an early algorithm. It only scales well for very specific problems. Variational algorithms are a rapidly evolving area, and more powerful methods like SQD and SKQD have been built directly on top of the principles you now understand: the variational principle, the ansatz, and the classical optimizer loop. You're now equipped to explore those and understand not just how they work, but why they're improvements. But more than anything, VQE is something you learn by doing. Head over to the module and try it yourself. Swap in a different ansatz, adjust the number of optimizer iterations, and see how the results change. And as a bonus, you can use the ground state energies you've calculated for the hydrogen atom and molecule to compute the reaction energy of H plus H yields H2. See you next time.